So for deterministic versus a probabilistic Hansen analysis, there's two very good reference on CAMFAX. Please read them. There's the Abrahamson 2002 and also the McGuire 2001. Those are classics paper to talk more in depth about like the two different like a design framework. And the main difference between the two are the results, like how time and very important uncertainty to be handled. So PSHAs account for four things that DSHA does not. First, the DSHA take also account into the more moderate earthquake rather than just one or a few large earthquake that deterministic approach would do. And also, the PSHAs will take account into the activity rates that will change from locations to locations. For example, the sand ages versus the new Marit at the Midwest will be very different. You anticipate the sand age forces much active to the maybe 10 times more active than the Marguerite fault in the Midwest. And also the ground motions, it will the predictions will can have more variability and uncertainty. It can even go up to 3 standard deviations. So we talk about when we get to the point to focus on the probabilistic approach to characterize the intensity measure. We talk about how to handle this uncertainties and by standard deviations. So for examples, like sometimes like why we take more account into the more moderate earthquake. For examples, if you have a magnitude like a 6.5 earthquake, but if you also consider the scenario that it has uncertainty, so you account for 2 standard deviations on top of this magnitude 6.5 earthquake, then it could be greater than because of the 2 standard deviations right there, could be greater than the magnitude equal 8 earthquakes. So when we list out all the scenario in the PSHA, you will see which one will have more like kind of like a damage in the case that is more like a worst case scenario, but you always balance out the uncertainty in a way that here, yes, you are pumping up the loading. You have 2 standard deviations, but you also take into account into the fact that this is rare. So the probability for this to be occur, the probabilistic that for this to be occur will be very small, versus like maybe this one. Yes, you have a magnitude of 8, but you are not considering the uncertainty in terms of the standard deviations. So you will have this scenario to be more frequent or more realistic, or like a higher probability to be happen than when you consider 2 standard deviations. So when we get to the details of PSHA, we'll talk more about it. And also the hazard level will increase when like more faults are considered. So we will talk about that too. And DSHA is the deterministic way. The deterministic method cannot handle this. So let's take these examples. For example, you have a site number 1 here versus site number 2 here, and site number 1 we make up the geology here. So we bring the Midwest to the West Coast. So the new Marit fault, for example, is 10 kilometers to your site with a earthquake magnitude 8. This is site number 1, and then now we bring this fault to California. We're just making up the geology here. So for example, it's like your site is 10 kilometers to the San Andreas, and kind of like a 5 kilometers, or make it 10. Both of them be 10. So this scenario. So this scenario here is the same, right? So both of them are 10 kilometers away from maybe let's say this is the new Marit fault instead of San Asia. So we kind of like bringing the Midwest like a fault to West Coast, just make like this 2 part to be identical. But for a site now, you have another earthquake fault, which is also 5 kilometers away from your site, the Hayward fault, and you have an earthquake magnitude of 7. So the DSHAs, if you just select the worst case scenario design, if you assume a one single, if you look at one lateral period, deterministic, you are able to combine two design spectrums to become like, we talked about this previously, to have the hybrid scenario for design that take the worst case scenario at different return period. So now, but if you only look at one return period, you always just consider the worst of one fault. So now if you have the worst, if you fixed it at one natural return period, and for deterministic approach, you can only consider one worst case scenario. So maybe this one will be the one from the magnitude 8 earthquake events. So pretty much if you do the DSHA deterministic analysis, you're ignoring the Hayward fault. But for the PSHAs, as we explained the procedure afterward, you will see it has the capability to consider both a scenario. So DSHA would give the same hazard for site number 1 and site number 2, where hazards means the ground motions without considerations of time and also probability. So PSHAs will be if we do a PSH analysis, then we will have the site 2 to be more hazard than site 1 due to the increased probability that I have an earthquake in a certain amount of time. So it will be an incorrect, a wrong concept that DSHAs always give you the worst case scenario analysis. Yes, it may give you the worst case scenario based on one fault systems, but it cannot give you worst case scenario when you consider all the fault systems that are being exist. So before we get into the details of PSHAs, let's talk about what is the final product, or what is the end results of PSHAs. The end product of the framework will give you the hazard curve, which is here, the hazard curve. So on the hazard curve, usually the y-axis will be in a log scale, and the y-axis will be the mean period or any weight of existency. So it's kind of it's a probability. It's talk about the weight of exceedancy, given that a different intensity measure on the x-axis. So this curve pretty much tells you a different intensity of loading, or this time is we choose PGA, peak ground accelerations, as the intensity measure. So at different level of shakings, what is the probability, or what is the weight of exceedancy for that to be happens? So that is the hazard curve. So after we do all the procedure or PSHA, then you should expect an all end product like this. So hazard curve will help us to predict what ground motion level we can expect to be exceed in a specific period of time. So the return period of a specific level of shaking. So the return period is related to the gamma here, the mean period rate of exceedancy. So the gamma is equals to 1 over the return period. So this is the return period here. So folks, some example is to speak of the risk level of from a hazard curve is something like 0.3 G. So this is the intensity measure. So you have a peak ground accelerations of 0.3 gravities, 0.3 times the gravities. It has an existing rate of 0.002. And if you do the reciprocals of the 0.002, give you 500 years, which means when you read this curve, means every 500 years you expect there will be a 0.3 G kind of shaking of earthquake. So that is the hazard curve. And if the level of shaking is higher, then you will have a lower weight, which means longer return period of time. So if you have 0.65 G, then you have a manual exceeding weight of 0.004 times the gravity. Sorry, not is 0.0004, so that corresponding to 2,500 years. So some common like a return period and the return period and exceedance rates usually in design. So it's very common to design for 10% probability of exceedancy, so which is like 0.1 in 50 years. And also ASHTOs, for example, is when they doing design for the bridge, they use 7% of probability of exceedancy. So this exceedancy is the gamma in 75 years. Okay, so for some common return period and the exceedance rate used in design, the common ones is the return period of 2,500 years and also 10% probability of exceedance rates in 250 years. So those are very popular design risk level. So with a return period of 2,500 years, usually those are very important structures. And in the older versions of IBC and ASC-7, sometimes they call the design scenario to be maximum considered earthquake, and usually this is the deterministic approach before the PSHA become like a popular. So starting in IBC 2012, you realize that the MCE now becomes like an MCE subscript R. So the R means the risk target, and so we see like there will be like a change, starting to change on the design codes almost like a decade ago, moving toward from DSHA to PSHA. So another PSHA design philosophy is that the design ground motions intensity are chosen based on the acceptable hazard of the project, and the hazard level is specified by the governing code. And the critical facility usually a design for higher hazard level. Okay, so what is PSHA? So starting on this slide, we'll walk through the framework step by steps, and don't be frustrated by the lengthy mathematical expressions or long formulas over there. So if you can break it down and understand like it step by step, it's just not bad at all. And this is a very powerful framework. And the major reference for this particular topic is this paper, the Baker paper 2008. So this is about like 50 page, 60 page of paper, but I highly recommend you to read through it. This is the best available reference that I have seen, and this Professor Jack Baker, he's a very well-known professor at Stanford. On pretty much his reputations and his major academic work is built on this PSHA framework, probabilistic approach for seismic evaluations. And he is a structural faculty, but he did a lot of good work in earthquake engineering. And your textbook may be a little bit outdated, but like the basic framework is still there. If you read your textbook chapter 4.4, you will also walk you through the basic concept. And this Professor Steve Kramer, he also very well known in probabilistic seismics has his analysis approach, and he pretty much is very focused on the geotech applications, and he even come out with a PSHA framework for liquefactions evaluations, and because of that particular work, he got a seat medal from ASCE. Which is very like prestigious prize in our field, and eventually I think he also got the Psyche Award, and also he also got introduced to NAE, so he pretty much got everything, all the through his academic career. He got all the academic prize and award that he academia can get. But anyways, so those are good read. So make sure you read them. So what is PSHA? So it try to quantify the whole framework. What you try to do is try to quantify the uncertainty in locations, size, and resulting shaking intensity. So that's three major part when we break down the mathematical expressions. So there's the locations, the size, and also the intensity. So we walk through all these three parts, which also like depicted on this picture. And eventually they consider all the scenario and also the uncertainty of each of them, and then they will combine them to be explicit descriptions, which is the hazard curve. So this hazard curve is the end product of all these mathematical computations there. So if we look at this framework again, so we try to consider the scenario of, again, the locations. So this term is the locations. So if you have different like epicenter of earthquake or different source of earthquake, so give you different locations, and if you consider all the possible locations and you do the integrations, so you try to combine all the scenarios. So same as the size of earthquake, which is the magnitude and the return rate of that particular amplitudes. So you have, for example, you have the Hayward Fault. If you look at one point from the Hayward Fault from our site, and you at the one point of locations give you constant distance, but but that particular locations, you could give you different magnitude earthquake. You don't know. You could give you a magnitude 5. You could give you a magnitude 6 or 7 or 8. So you have a different magnitude earthquake associated with a different existent rate of that magnitude. So if you have design for a magnitude 8 earthquake at Hayward Fault, that will be very rare. So you have a lower probability for that to be happened. But if you design magnitude 4 earthquake from the Hayward Fault, that could be quite frequent. And then the probability for that happens to be higher. So you have all these different combinations, and you consider all of them, and then you do the integration. So you kind of like consider all the possible cases. And last but not least, this one may be a little bit more complicated, is the shaking intensity represented by an intensity measure. And also you need to consider standard deviations for that. So one common intensity measure that we can use is the peak one accelerations. So you consider those three category, and then you combine all the scenarios from each category. Then you could imagine in Southern California, because you have so many different possible fault systems or earthquake locations that to be happens, and you have also different magnitudes that can be associated with that. And if you combine all the scenario easily, you can get combinations of possible combinations of 1,000 or 2,000 scenarios. But if you can do it, set up computations tool or spreadsheet, or you program it, and the calculations won't too bad. But this class, what we would do is we would try look at just a couple scenario, such that you can do your math on a paper, or or like, if you look at a little bit more complicated, like a semester projects, then you may need Excel spreadsheet, with a handful of scenario, maybe 5 or 6 or 10. Then you get a chance to walk through the whole PSHA's design methodology. So if you integrate all this probability, you get the overall probability for the intensity measures that you're designing greater than a certain threshold. So this could be, if you're using PGA, this could be 1G or 2G. So this graph over here pretty much like tells you like the expressions over here. So the very first step we always to do is to identify the earthquake source. So I would say this could be a seismologist like a work class here. And then like this graph pretty much is representing the characterizations of distributions of earthquake magnitudes from each source. So remember we talked about the Gutenberg and Richter formulations of 1944 back to lecture 1, maybe lecture 1, lecture 2, I think it's lecture 1. So this is like tells you at different earthquake magnitudes what is the any rate of exceedancy. So we talked about this before. So this kind of like a probability. This any rate of exceedancy. So this is just one of the. We'll get to there on next slide. But like this is pretty much this tells you the earthquake size, which is this terms here, and also you consider the locations. So if you have a probability density functions, at like a certain distance away, how large is your circle. If you draw boundaries, the larger the circle you are, the more likely you will cover the fault systems. So this is the probability density functions for the locations, and this is the earthquake intensity. So now this is the PGA, and how far away from the source of the earthquake. So this is the characterizations of distributions of source to site distance. So again, like if you're really close to the earthquake faulting area or the earthquake source, you expect a very high loading. So you have a high peak ground accelerations right there for the examples. And if you're further away, then the shaking intensity will be much smaller. And there's a lot of uncertainty to have associated with it. So you want to also characterize the intensity in terms of standard deviations or probabilistic characterizations using the normal distributions. So you can use other distributions. You can use a log normals, but based on how you want to simulate your uncertainty and also earthquake loading. But normal distributions, like for this applications, we were fine. So if you want to have one duration of a loading that is one standard deviations above, so you have a less chance. So on this graph here, so this is pretty much, if you just look at this property density functions, so this is probability, right, the y-axis. And also here is the loading, the peak ground accelerations. So if you just look at this distributions, so this is the PGA. So which means like the higher loading that you get here, you will be less probability. The most probability is the most chance happen is right at the median. And if you want to lower than that, then the chance will be less. So we talk about that more when we get there too. But like at this, in the following slides, we will talk about each of them individually. At least these three slides, these three categories. Again, this is the magnitudes, this is locations, and this is the intensity. And combining all these three categories, you do your integrations here. Then you get the probability for the intensity measure that you are looking at. greater than third threshold. And then if you have this probability multiplied by the rate of occurrence, so this was given here. So this is the rate of occurrence. Then it gives you the any rate of exceedancy. So here, so this part here pretty much is this part. So now finally you get the rate of exceedancy, and this x here is one particular ground shaking they're looking at. So for example, if you design for PGA equals to 0.2, so the x here is 0.2, so you do all your calculations right there. So x is 0.2 at different scenario of magnitudes, distance, and so on and so on. Then you do the integrations, then end up you get at 0.2, you get 1 point here. So finally you get like 1 point of the correspondence of the any rate of exceedancy. And if you repeat the procedure and then you pick like a 0.5 as your ground shaking level you're investigating, then you get the corresponding any rate of exceedancy. So this graph or this curve, this hazard curve, at the end of the day, again, like our final product is the hazard curve. So this hazard curve is generated by the formula here. We'll do some examples at the end. So next we will talk about each categories, and then like from there we do a couple examples and walk you through how to establish this hazard curve. So hopefully, like get to the point that when we do the examples, everything will be much clearer and also start to make sense to you. So this is the basic framework in terms of the integrations. And the whole thing can be discreted because we will look at like a different scenario instead of like a continuous functions. Like for example, I consider the earthquake magnitudes from 5 to 8. Instead of continuously from 5 to 8, we can discrete our steps maybe to 0.5. So you look at scenario of 5, 5.5 and 6 and 6.5 and then 7 and 7.5 and 8. So we discrete the magnitude step of 0.5. Then the whole thing can become like a discretions. So here is the same framework as what we are seeing here, but now it's just like based on like a different discrete scenario, but the same thing. Again, the locations, the magnitudes or the size, and sorry, this is the location. So this is the locations. So this is the size, and this is the intensity. So 3 categories. Well, provided that like the geologists have helped us to identify the earthquake source already. So based on each earthquake source, we consider again the locations, the size, and intensity, and we sum up all the possible scenario. Then you will get the rate of exceedancy when you multiply with the rate of occurrence. So so this is kind of like the probability again, and then times the rate of occurrence. Then you will get the any rate of exceedancy. So hopefully we get there in the examples. Then this will start seeing the numbers. You will this will start making sense to you. But next, we talk about our first case scenario. So we talk about let's talk about the size, or what we call here is the magnitudes of the earthquakes. So let's talk about this this term here, the earthquake magnitudes. So on the Baker 2008 paper, they describe about they spend I think more like a space to describe about the Gandenburg and Wichita 1944 model, which is not bounded. But here, like I try to walk you through the math on the bounded one. So the 1944 model is a good start, but the major shortcoming is it didn't cap at the higher magnitudes. According to the models, like the magnitude earthquake can go larger and larger without limits. Even the probability of chance for that to be happens, but you can go according to the models. You can go the magnitudes go for 10 or go for 20. That's insane. That's no way to for that to be possible. The Earth will will explode before we get to that huge amount of energy. So the bounded or the capped or the truncated Gandenburg and Richter models will give you cap it by the maximum amplitudes. And remember, this is the equations for the models. So the annual rate of exceedancy here, the gamma m, depends on the magnitudes, and then dictated by two parameters, which is like a site-specific parameters, A and B. So what they do is they just do curve feedings based on historical data, and the A and B are the curve feedings parameters to describe or to relate the earthquake magnitude with the annual rate of exceedancy. And if we work around our mouth, like to move, take out the log, then the annual rate of exceedancy will be equals to 10 to the power A minus B times the earthquake magnitudes. So now we want to establish a cumulative probabilistic density functions for that. So which means we want to find out the probability of the magnitudes is is greater than a certain desired level, given that this desired level is capped by the maximum possible earthquake and also like a minimum threshold that you want to look at. So for example, your structure can handle magnitude of earthquake 5 without problems. So your minimum earthquake magnitude could be 5. Or very likely, if we have a magnitude earthquake of magnitude of 3, there will be no feeling at all. We don't feel anything, same as a structure. So this is the lower bound, and also you have the upper bound. So again, you look at the design magnitudes based on further thresholds, and the magnitude thresholds should be bounded by your maximum possible and also minimum level that you care. So which means this probabilistic density functions is the rate of earthquake between is capped by the one that you want to look at, the magnitude that you want to look at, between and then greater than the minimum. And also this one is given that this is between the possible max and also the possible mean. And if we do the math here, or express this in the annual rate of exceedancy, you will be the gamma mean minus the gamma m, and also the gamma mean minus the gamma max to describe this two scenario. And we know the annual rate of exceedancy, you have this model. So if you plug in these equations into this number here, so if you plug in this part into there, then we get the equations right on this part. And now if you divide everything by this part, you work on the math, then you will get the cumulative density functions. And if we want to convert that to be a probabilistic density functions, we do the derivative. So we differentiate this equation here once, and then we get the probability density functions. But for our applications, pretty much if we want to calculate probability of magnitudes of a certain level, then we will calculate, pretty much like by this using this formula. So the later examples, we will do a couple real design scenario. Then hopefully, like, when we plug in a number, this will make sense to you. So because this is cumulative, so the probability density functions, or in other way, instead of like differentiated, you will be discrete like expressions. You'll be just the difference between over the two. So for example, if I have earthquake magnitudes of 5, and also a 5.25, and and a 5.5, so forth and so on. And when I calculate all those like cumulative density probability, so for example, for this to be happens, earthquake 5 that to be happens, for example, this is 0.1, and this is a 0.15, and this is like a 0.16, and because this is cumulative, so the number should be getting bigger and bigger. And if we just look at the particular design scenario of earthquake 5, and for the probability for that to be happens, or like we can call this to be the probability density functions, then here pretty much is the next one, the cumulative one minus the current one, so which is the formula here. So here will be 0.15 minus like 0.1, and this one will be 0.16 minus 0.15, so 0.01, and you will need the next one to calculate this one. So so that's the idea of between the cumulative like density functions and also the probabilistic density functions. So if you need more background on statistics on like a probabilistic basic, I think the Baker paper at the end, they have an appendix, same as your Kramer textbook. It has an appendix to talk about the basic probabilistic knowledge. So feel free to review them. I think you better review them too if you want to do well on this topic, PSHA. So that's the basic of the size that of terms we want to talk about in PSHA, and we'll come back to it when we do some examples, and hopefully, like when you see the numbers, you will make more sense to you. Okay, so the second category here is the locations. So we are working on this part of the PSHA framework. So for the source of earthquake could be 3 different types. It could be an area, could be a line, or could be a pond. So a pond will be easy, so you don't have any like uncertainty, because a pond to your site, a pond to a pond, you only have a fixed distance, and that gives you pretty much like a probability of 1. So you will see that happens in some examples, because we want to simplify the scenario for you to pick up. So the very first examples that we look at together, you will be just a pond source, and on the Baker paper, you have like explanations for the line source. So I encourage you to read that. Here just demonstrate quick examples on the area source. So for example, here you have a circular source, your site is right there, and you consider if you are 100 kilometers away, if you draw circles that like 100 kilometers like from the site, you are pretty sure is you will cover the area source. So that case, like you have a probability of 1. So those number here, y100, like y like the locations of the sites and the locations of the epicenter, that could be dictated by that could be provided by the geologists. So here, as engineers, we just come up with the probability. So if the cover area is large enough, for sure we'll we'll cover the earthquake area source if like this distance is 0. then there's the probability is 0. But like if it's an in between, that would be the area of the circles divided by the area of the certainty of 100 kilometers. So that gives you the cumulative probabilistic density functions, which is this one, by the formula, and then you can plot out the cumulative probability functions, and that would be going into your earthquake distance PSHA part of it. So the third is the ground motion's intensity. So the IM, and in these examples, I picked the PGA, peak accelerations, and later on when we get to the uniform seismic hazard curve, then that case you want to develop not just one period, but you want to develop like a system of period. Then that means like a spectral accelerations. Then you will look at other like a period response. Here we just the examples quick and simple. Just look at the peak one accelerations. So the intensity measure will be a matter of magnitude and distance, and also the standard durations right there. Keep that in mind. And those intensity measure and also standard durations in common practice is from the NGA model, the next generation attenuations model that we talk about in the previous lecture 2. Remember those Abrahamson and Silver and Idris models. So those are where you can get the intensity measure with uncertainty. But the examples, and also the same as the Baker paper, we look in much symbols attenuations model, which is the Cornell 1979, with this equations there. So I picked those equations just because this is simple enough. This is really outdated equations. I doubt about like anyone still using that in practice, but I picked this one, and I think I will ask you to use this one for homework too, and likely maybe in exams. Maybe I find one like with the similar simplicities, then I will ask you to do it. Just because I picked this one, just because it's manageable for you to calculate by hand, or a simple formula in Excel. Remember, those attenuations models, just the formulas, you could have like 25 or even like 100 coefficients, and those are not possible to do it by hand. But this Cornell is manageable. So this PGA here depends on the magnitudes and the distance. And if you apply these equations, this will give you the median. So this will just give you the mean, or the median PGA. So this is median, which means whatever you calculate here represent this center line. In terms of the distance. So this is what these equations mean. But just this equations and this line here is not enough to describe the probability, because everything is about a probability, and the probability over there is represented by this distribution functions over there, which is a normal distribution functions. So it could be any distribution functions. If you go back to your statistic cards, you could be log normals, you could be another like a log distributions. But here we choose the normals distributions. When you do this, it highly depends on which model you use. And I think most of the models are normally distributed, but I cannot say it's 100% it's always normally distributed. Depends on, again, the GMPE models. So when you use those models, you need to be very careful to understand how they capture the uncertainty. But this Cornell models, they use the normal distributions. So if this gives you the mediums, and you know this is a normally distributed functions. So at certain like a PGA or the at certain like given the mean, and like so kind of just like a statistic problem here now. If you know the mean, so if you look at like this particular like a curve right there, you know the mean, and also if you know the PGA that is away from the mean or the mediums, then like you can find out the probability through like the simple normal distributions calculations. So here, for example, if you want to know about the peak one accelerations that is greater than certain like level, so it could be like somewhere like along those distributions, and then at the given magnitudes and also distance, then you can calculate the probability based on that. So the probability, this is pretty much as the normal distributions calculations for the probability. So you have the value that you're looking at, the x, and then this is the mean the medium. So whatever you calculate here goes into this functions. So this is the mean. So whatever you are calculating respect to the mean and also the standard deviations, so this should be given to you. So that this standard deviations tells you how wide how short and flat the models, or how narrow, tall, and like close to the standard type of like a distribution. So this is dictated by the standard deviations. So again, this is basic statistics. If you need to review like those like a statistic background, I highly recommend you to to go back to crack your statistic book, or go to the Kramer textbook appendix to refresh those like standard deviations and normal distributions, those concepts behind. So if you plug in those numbers, and then like you can calculate this either by Excel or use those like a standard statistic models about normal distributions, or use MATLAB, then you can calculate this number, and at the end of the day, this will give you the probability. So some examples, for example, you have a magnitude 6.5, and also you have a distance 3 kilometers, 10 kilometers, and like a 30 kilometers array. So this should be a comma. So we are fixed the magnitudes here, but if we change the 3, 10, and 30 kilometer distance away from your earthquake source, and you are designing for the peak one accelerations for 1G. So pretty much like the target intensity measure is fixed, the magnitude is fixed, but the distance is changing, then you will give you different probability for that to be happens. So because like if you change the distance, right, pretty much along this median curve, you have different PGA. So for examples, like if we plug in a 6.5 into our Cornell equations, and also plug in distance equal 3 in our Cornell equations, then we calculate these equations, we will get this number. If again you plug in 6.5 and 3 into these equations, you will get a log PGAs equals to negative 0.5765. And our x is 1 because we are looking at the PGA equal 1. So we know this, we know that, and given that the standard deviations for this Cornell models is 0.57. So this is the log PGA is 0.57. So you plug in here, then you get to this, you calculate this is equals to 1.01, or if you have these functions, you don't want to use those like standard deviation tables, you want to use Excel. So in Excel you would use the these functions, the norm, this functions, and then you will put in log 1, put in the mean, which is like a 0.5765, and you put in the standard deviations. So this is the number you look at, and this is kind of like the mean or the median, and this is the standard deviations. And if that with that, the Excel should return this number, and if you 1 minus that, then you get 0.16. So this is the probability. Again, this means the probability of at the distance like a 3 kilometers away. So if you have 3 kilometers here, and like and then you have so what graphically means here, for example, you have like 1, 2, 3. This is the 3 kilometers, and if you go to this curve, not the probability, but like the PGA corresponding to that will be the anti-log of this number, and you want to know at like the PGA equal to 1 at this distance, and the magnitudes, corresponding magnitudes at this particular like probability right there. So probability means like this part of the area. So for the entire area here is equal 1, but just for this part, for the probability of exceeding that at PG equal 1 at this mediums and this like a distant array, what is the because this is like a probability function. So the y-axis, this is the probability functions, and pretty much this is at different like a PGA level. So this is like kind of like a PG equal 1, and if you calculate this area, then that would give you this probability. So that's the concept of characterizing the probabilities of ground motion's intensity. And if we repeat this with different distance away, so we also look at a 10, this at this r equal 10 array, and then like we look at like a PG equal 1 again, then we will calculate this area again, and also look at 30 is here, and then now we calculate another area of probability. So the probability getting smaller and smaller, because like when PG equal 1, it's just like a tiny bit here. So that gives you a really small probability for that to be happens. So that's the concept of how to make use of GMPE, the ground motion prediction equations, which is this case the Cornell equations here, and then in conjunction with the normal distributions to describe the probability inside the PSHA framework. So more about this is like we talk about the PGA level, but in our PSHA's analysis, we will consider all different kind of intensity measure. Here we fixed it at PGA equal 1, but in design, you could be like however many you want, or like you need to make the judgment call what kind of like intensity measure, and what is the descriptions, how small the step you want to consider for each scenario to be think of. So for example, here like they consider like a different PGA level, 0.2, 0.25, 0.3, 0.35, 0.4, and pretty much you repeat the procedure. So now this X is changing to instead of 1, you do it for 0.2, 0.25, 0.3, 0.35, 0.4 for a given like a standard magnitudes and distance. So magnitude and distance, so they could be all the same, but like you just change the PGA level. So 10 kilometers away, and the magnitude 6, you consider different type of peak ground accelerations, and then you calculate the property that associate with that like a pair of magnitude and distance. Then you get like different scenario, and then like both, and you have a big summations right there, right, for the framework PSHA. So at the end of the day, you will sum up all the scenario, and then that represent then 1 point of your hazard curve. So that's the idea of the PSHA. So you can imagine there can be many different scenarios, because now you're fixing the magnitude distance. So for example, you can have something like this. So magnitude, distance, magnitude and distance, and PGA. So each scenario, so you have like a different scenario that based on these three parameters, and each like parameters, you will come up with the probability. So at the end of the day, you come up with the probability of each like a design scenario. So here, for example, you consider like a PGA of 0.3 and 0.6 and 1 at one, like, you know, one like a standard magnitude and distance, and then you will repeat the procedure, perhaps at different like magnitudes, the same distance, and then you calculate each case. You calculate the corresponding probability. And then like after that, like, you know, you have this patterns of magnitudes and peak accelerations. Then you change the distance, so that you can have many different scenario, and you try to capture all the possible scenarios. So at the end of the day, you know, it's very powerful tool. So you combine all the cases, then you will get your annual age of exceedancy for that calculations. So that's pretty much the basic framework for the PSHA. And overall recap again, the whole concept is to try to incorporate the locations, the size, and also the intensity of earthquake, and then, like, you know, each of them is captured by the probability, and both the magnitudes and distance, and also the intensity. And then you create all the scenario. You imagine, like, you know, your semester project will be huge, not like huge, like, you know, I don't think you are asked you to do many different scenario, but maybe the extra credit that are given on the semester project will be a little bit more scenario that you need to do. So at the end of the day, you sum up all of them, then you will get the annual wage of existency. Okay, so example 3. So this one is a bit more complicated, in a sense that now the magnitude of earthquake is not fixed. But the good news for this one is the distance is fixed. So you have a point source of earthquake that you don't know the amplitudes, or, like, you know, you need to consider the different scenario of magnitude for that. And the rate of occurrence still constant is equals to 0.02. So if we look at our framework for PSHA, the rate of exceedancy for the PGA, so intensity again is PGA, you know, it could be anything else. It could be the spectral accelerations at different natural period. It could be intense aerial intensity. But now we just look at PGA, assume it's just greater than like a level that we're looking at, and then that will equals to the rate of occurrence times the intensity measure. So the intensity measure, the probability for that this time is the PGA, and it depends on both the magnitudes and also the distance. It was a constant in the previous examples. It was like a magnitude 6.5 and a 10 kilo, you know, is a 10 kilometers. So those are constant, but now it's not necessarily constant. So that's why we have two warning index here now, one for the distance and one for the magnitude. So this is the magnitudes and this is the distance. And for this case, we have a point source of earthquake, so the distance still constant. So this is 10 kilometers again. So we have this become a constant, but yet we need to take care of the uncertainty or the probability of the earthquake magnitudes, and we talk about how to do that. So the PSHA framework, right, is also come with the magnitude terms. Now it's no longer a constant equals to 1. And also the locations. This one, our distance is constant. So this is equals to 1. And this part is equals to 0.02. So we need to take care of different scenario now. And so to clean this up, this PSHA framework for this particular examples would be equals to this. So the magnitude is just changing, but the distance is constant, and times the probability of the earthquake magnitudes. So this is our PSHA framework for these examples. And we use a discrete scenario. So the first step to do is to break this down into a different component, and it depends on the magnitude earthquakes, the scenario of different amplitudes. So let's assume this site has minimum earthquake of 5 to be considered for design. So we cap the minimum magnitudes of earthquake is equal to 5. So we use 5, and we use a step of 0.25 to do our analysis. Oops. So forth and so forth, and we can keep it to it until like a 7.75 of earthquake magnitudes. And we need to take care of different components. So first we need to take care of the noting amplitude part. So the first we need to think of how to characterize, or how to come with the probability of the earthquake magnitudes. Remember, we learned about the Gutenberg model for the earthquake magnitudes, which is this one. Yeah, which is this one. And if you go back to the Jack Baker paper, 2008, he has the bounded Gutenberg and Richter, and also the unbounded one. So the example show you the bounded one, a little bit more complicated. Let's use the unbounded one. That will make your life a little bit easier in terms of hand calculations. And the cumulative density functions for the probability for this model is this one, equals to 1 minus 10 to negative b, the magnitudes minus the minimum considered earthquake. So this is equal to 5, and the b, assume this is 1. So this formula here gives you the cumulative density functions for the probability. So we can take care of this part here now. So we can calculate the probability. So this is the cumulative density functions. So the first one will be 1 minus 10 to negative 1, 5 minus 5. Because we're looking at the scenario of magnitude equal 5, and we know the minimum earthquake for that is 5. The minimum conceivable magnitude earthquake is 5. So this is 0, and then the next you will do the 5.25 minus 5, and this one you will get 0.438, and then so on and so on. I keep like plugging the magnitudes that you're considering. For with 5.5, it is 0.6845. So after we calculate the CDF, so just keep go on. So after we calculate the CDF, then we can convert that to the property density functions. So if this is a continuous functions, then we will do the derivative. We differentiate the CDF to get the PDF. But if this is discrete one, in order to change the cumulative back to the one that you consider at a particular interval or particular descriptions, you will do the next step minus the current step. So what does it mean is this equals to the next step minus the current step. Then you can get the PDF, the property density functions, which means like, examples. So if you look at like earthquake magnitude equal 5, the current cumulative density functions is 0, and the next step 5.25 is 0.438. So this one will be the next step minus the current step. So at 5.25, then you'll be like the next step 5.5, which is 0.6845 minus the current step 0.38. So you will get those number. So here is 0.438, and here will be equals to 0.2465. So this help you to take care of and again, like so forth so on. You need to keep this going. So you can foresee, like, you better do this on Excel. Otherwise, like, hand calculations is very hard to keep track with all the different scenario. And easily, like, for example, like this, in order to establish the hazard curve, you need like almost like 100 scenario in order to establish the point that you need. But anyways, after you calculate for the magnitudes like a probability, then we can move on to the PGA for the intensity function, the intensity measure. So then you have this part. So first, like we take advantage of the Cornell equations one more time. So the log PGA, and we are designing for a distance that is 10 kilometers, 10 kilometers away, and we look at our first magnitude scenario, which is 5, and then if you plug in the equations again there, so magnitude is 5, and the this distance is 10 kilometers. So again, this is, we repeatedly use the Cornell equations just because this is relatively like straightforward in terms of the formula. And this is outdated attenuations equations. In practice, people use the NGA model, the next generation attenuations. But anyways, like you got those numbers, and then you get your PGA median to be 0.1036. So what I'm doing here now is just the first scenario, and I'm trying to calculate the probability for PGA greater than x, and here now I need to pick my x. So remember, like at the end of the day is the hazard curve. That's the final product. This is PGA, and this will be the exceedance rate. So, and let's pick one pond, pond 2. So imagine, like you need to take many different ponds when you do the to complete the whole hazard curve. But now we just look at one pond. Let's look at the pond 2 G right there, and this is given that the magnitudes is changing, and also we have the constant distance, which is 10 kilometers. So we try to calculate that. So in order to calculate this part, then particular for the magnitude equal 5, so this now is like a PGA greater than 0.2 G, given that the magnitude is 5 and this 10 kilometers away, and this is a probability with normal distributions, and if we do our probability calculations again, so this x is 0.2, and the mean is like a 0.0136, we just calculated like previously, and one more time, it's like the standard deviation is 0.57, so this should be given to you at the beginning when like the earthquake source is identified. So if we do this in Excel or like any standard chart that you have for statistic, this is 0.1243. So which means like this calculations give you 0.1243. And we will repeat this procedure again, but now when you go down the row on the tables, now it's 5.25 and the next is 5.5. So you will plug in like this 5 here become 5.25 and 5.5 and so on and so on when you move down the table, and then you need to update like your probability based on you have a new mean here. And the next one you got, if you do all the calculations correctly, this is 2185. So pretty much like we have these two steps already, and eventually if you want to combine or like find the major product here. So if you want to find out this particular terms, at the end of the day, this one is what you calculate on your to become the final answer or the y-axis for the particular point 2 you're looking at. So pretty much like this total table that we are working on now is for the 0.2 PGA on the hazard curve. So the whole table will just give you pretty much one data points. And if you need one data point, if you want more data points, then you need to repeat the tables of the tables. So you need to do a couple tables in order to for you to able to establish the hazard curve. But anyways, so this is what you get, and eventually, like you want to calculate this range of exceedancy right there. So this part here will be equals to whatever. So let's say this is column 1, column 2, column 3, and column 4. So in order to get to this point, this will be the rate of occurrence here, alpha, which is 0.02. There's a constant for the sites. You should come with the geologist, give you this number, and then this multiplied by so this green block here is column 4, and also multiplied by this one, So this is column 3. So you will get like the exceedance rate at like the first scenario with earthquake magnitude of 5, and then end up you will sum up with all this number. At the end, whatever you get here will be the corresponding point right there. So this number eventually you got at the summations at the end will becomes, whoops, your data point that you have over there. And this is just one data point, so that's why like you need to change your PGA to another level, and then you get another data points with another table. So that's why like that's something that you better do on Excel, and then if you can automate this, and people can write a program about this too, then the hazard curve will come out more robust and more easy in a way that like the spreadsheet do the calculation for you. But like to get there, you need to fully understand the framework of PSHA and how to get to those numbers. Okay, so let's do our quick examples together. So this examples is the first one, so it's the most simple one. You come up with a source of earthquake with a single magnitude and distance. So here you have your site, and also you have your fault. And it's given that the magnitude is 6.5, and the rate of occurrence of the earthquake is 0.01. So pretty much the magnitude is fixed. The locations is fixed too. So we assume like the epicenter only happened at one point. So it's a point source. It's a point source that's exactly 10 kilometers away from our site. So try to keep things simple here. But what happened is the earthquake intensity, which will be characterized by peak ground accelerations for these examples, can be different. So we know the magnitudes and we know the distance, but the PGA can be different. And we will use the Cornell method that we talked about previously. So we will use these equations, the Cornell equations right there, again for our calculations for intensity measure. It's something not totally outdated, but something simple enough that we can do a hand calculations. So first, let's based on the given informations, we can find the median PGA. So the log PGA, if you plug in the Cornell equations, 0.859, and we know the earthquake magnitude is 6.5, and then minus the 1.803 log the distance in kilometers plus 25. So if we do our math, the median will be equals to peak ground accelerations will be negative 0.979, and also we assume, or this will given to you, so this should come up with like part of the earthquake source characterizations for the standard deviations for the noting the intensity measure. So in the exams homework, I will give this number to you. So the associate probability or the uncertainty come with this equations, and also for this site is 0.57. So if we do our math, if we do our anti-log here, it will be equals to the median peak ground accelerations is 0.3758. Okay, so next, look let's look at the PSHA framework. Remember, there's like a three parts, right? So the equations for the PSHA. So first, the wage of exceedancy. Now we look at a PGA greater than a certain like a level. We will decide that later. Will be equals to the wage of occurrence, which is given by U as 0.01 in this case. The wage of occurrence for our earthquake magnitudes greater than the minimum level, and then times, remember there's like a 3, so which exactly is just this equation here. And there's a 3 part, right? The loading intensity, the magnitudes, and also the distance. So the first part is the loading intensity of the PSHA. So it's the PGA greater than certain level, given that we have a 6.5 magnitude earthquake, and this is 10 kilometers away. And the next is you have the magnitudes, or the size of the earthquake. Oops. Which is expressed in magnitudes. So magnitudes equals to 6.5, and also we have the distance, which is 10 kilometers. Since this is only a single source and a single amplitude, so the probability for the earthquake magnitudes equals 6.5 is 1, and the probability of the distance of the locations to be 10 kilometers away from our site from the earthquake source is also 1. So we try to keep things like a symbol here. And the wage of occurrence, this part is given 0.01. So end up like our wage of exceedancy, the probability is highly conform or just depends on the intensity measure part of it. So if we just look at this part, that will be equals to the probability of the PGA, which is greater than x. So x is our intensity measure level, is a variable in terms of PGA, given that like the magnitude is 6.5 and the distance is 10 kilometers, will be equals to 1 minus. This is a normally distributed property density. So if we use the probability with the normal distributions, so this will be the log x minus the median values divided by the standard deviations. So this is the standard deviations right there. So from this, if we calculate like this property functions with different x, then we can working toward end product. So I forgot to mention this at the beginning. So what is the final product of this exercise, or what is the answer? What we want to get to for this PSHA examples. Remember the end product of the PSHA is the Hasse curve, which means that we should come out with the x-axis to be the ground motion's intensity. In our case, is PGA. So that's why our PGA is x, because different PGA we have different associate and the wage of exceedancy. So pretty much back to our examples. The x here will be our the x here will be our final answer x-axis, which is the PGA, and the y-axis will be the annual wage of exceedancy, which is this part. So this is our y-axis. and this is our x-axis in terms of our final answer. So if we so don't be confused between the rate of occurrence and also rate of exceedancy. So this is the rate of exceedancy for the intensity measure. So what we need to do now is pick some x values, plug in our equations, which is here, and then we calculate the rate of exceedancy. So first, maybe let's assume first we pick x equal 1, so the PG equal 1. So this will be in terms of a G gravity. So we plug in this equation here. Then we try to find the probability for the peak ground accelerations is greater than 1 to that happens, given that the material is 6.5 and the distance is 10. And if we plug in these equations, or plug in this normal distributions calculations, so pretty much this is 1 minus. So this sign here means the normal distributions, not 1, right? And then minus, we calculate the mean PGA already, which is this number here, negative 0.979, and then divided by, so this is the sigma. The standard deviation is 0.57. So you can either do it on Excel or you can do it with the standard normal distributions chart. So maybe if I try to do really quick on Excel, let's try to do it together. If I try to do it in Excel, for example, so if I do it in Excel, the function for that is norm this, and then first I will put in the log 1. Whoops. So this is my x values, and then I will put in the mean. So the mean is a log PGA. So this is negative 0.979, and then put in my standard durations, and my standard durations is 0.57, and put in the true. So this will be my my probability for the density functions, and 1 minus that will be, oops, what I need to find out. So it's 0.43. So if I go back to my answer now, so this part will be equals to 0.043. And for the rate of exceedancy, so if we plug in these equations now, so this is my PSHA framework. So if I plug it back there, so the rate of exceedancy for the PGA greater than 1G will be equals to my rate of occurrence, which is 0.1 times my so that's again the 3 part, right? First is the intensity measure, the probability for the given scenario. We calculate that is 0.043, and then now the probability for earthquake magnitudes of 6.5 to be happen is 1, and the probability for being 10 kilometers away from the source of earthquake is 1. So with the whole thing now, I calculate not the probability, but the rate of occurrence is 0.00043. Okay, so I got my first pawn at like a PGA equal to 1, and then the corresponding rate of exceedancy is 0.00043. So this is my first data point. So I will repeat this procedure. For example, like the next one, I got like the PGA. Let me pick the point of 0.375. So now I pick another point over here. So PGA greater than 0.375 G, given a magnitude of 6.5 and a distance of 10 kilometers away. And if I plug in the whole thing into my probability equations, which is take advantage of the normal distributions. So now this is log 0.375, and then like everything is still the same. The log mean of the PGA, the log PGA is negative 0.979, and then divided by the standard deviation is 0.57. And if I do it again on Excel, or you use the statistic chart, I got 0.5. And so knowing the probability now, I can calculate the rate of exceedancy, but this time is 0.375 G, equals to the rate of occurrence times the probability, which is 0.05. So in this case will be equals to 0.005, so a little bit higher, which makes sense because now you have a lower intensity measure, lower level of shaking, so the rate of occurrence will be higher. So if you keep on repeat this procedure, then you will get like enough data point, then end up you can plot the hazard curve. This is your final answer. So you need more data points to make a curve. Okay, so example 2. So now this example, we try to step up a little bit with an extra fault B right here. So this part, the fault A, and for distance from the site is exactly same as the previous examples. So what happened now is we just add another fault over there for our PSHA analysis. So we have fault A and fault B. And fault B, you have a magnitude of 7.5 and rate of occurrence of 0.002. So those numbers are different from fault A. Plus this is a little bit like farther. So this is like 20 kilometers away. So if we want to establish, so I put the end product here. So this is the final answer, but I want you to walk you through how to get to this final answer, and realize that there's two faults. And fault A, the hazard curve that we get there will be exactly same as the one that we developed in the previous examples. So but now we have fault B, and let's see what happens. So for fault B, if we plug in again using the same procedure, using the Cornell equations to find the median PGA will be equals to negative 1.152, 0.152, and then plus 0.859, and then this is the magnitude is 7.5 this time, minus 1.803 log the 20 kilometers array. plus 25. And if we do our math, the mean we unlock it already. So the PG is 0.5639. And if we plug in or if we try to find the probability, so let's look at two different like shaking level. So let's look at the 0.375, the previous like PG we look at, and also we will look at PG equal 1. So for the case that the probability for this fault number B for the PGA greater than 0.375, given that the earthquake magnitude is 7.5 and a 20 kilometers away, and if you find the probability using the normally distributed functions. So first, this is the mean. No, sorry, not the mean. It's the x values that we are looking for, and then log. This is the mean, 0.5. That we just calculate. So 0.5639, and divided by the standard deviation. So it's the same standard deviations as the previous one. So if we calculate this, so that will be give us the probability for fault number B. But if we look at the whole systems for the range of exceedancy for PGA, that is greater than 0.375. And again, the magnitudes, there's two other parts for PSHA, right? The magnitudes and also the distance for each of this fault are constant, so the probability for them are 1. So if we look at the whole systems, so this will be equals to 0.01, right? This is the range of occurrence times 1, which is the probability for a magnitude equal to 6.5, right? Our first earthquake, first fault, and then like the distance, the probability for that being 10 is 1, because we only have one one scenario that we consider, and then you will be times the probability that for the PGA, which is greater than 0.375. And then given this is a 6.5 earthquake and 10 kilometers away, so this makeup will be our fault A. So we calculate this part already in the previous example. So this will be exactly same as the number there we calculate. So this is 0.005 right there. So exactly same. So the fault area, right? So we'll be here 0.005 that we have already calculated. And so for fault B, the rate of occurrence this time given is 0.002, and then again the probability for this is a 7.5 earthquake is 1, and the probability for the distant array 20 kilometers array is 1. And then now we multiply by the probability that the PGA is greater than 0.375, given a 7.5 earthquake. This is fault B, and 20 kilometers away. So which is this part that we find out right there. And then if we the previous one, if we find the Parkinson number is equals to 0.761. And this part, the whole thing here is fault B. So if we carry on, like, the calculations there, the rate of exceedancy of the peak 1 accelerations is greater than 0.375 for both fault A and fault B. So this will be the rate of exceedance is 0.01 for fault A times the probability that we calculate is 0.5. And then for fault B, the rate of occurrence is 0.002, and then times the probability for the scenario to be happens is 0.6761. And then if we calculate the whole thing, then this will be equals to 0.00652. So pretty much just like, we add up these 2 points, and we got this value there. So, and if we also repeat the procedure for at 1G, so for the probability that, let me do it here. So that's why let me do it here. So for the probability for PGA greater than 1G for fault B, it is a 7.5 earthquake and 20 kilometers away. And if we plug in the normally distributed equations, so this will be the x value log 1 minus the log of the median that we calculate, which is 0.5639, and the standard deviation is 0.57, and this is 0.1574. So for the rate of exceedancy for PGA greater than 1, for both fault A and fault B will be equals to 0.01 times 0.044, and then plus 0.002 times 0.1574. So we got 0.000746. So those numbers are small because the chance for earthquake to happen, is not that high. But there's something we need to find out, or we need to estimate. So this is the number here. Oops. For this point at 1G. So you will see, it verify what we mentioned previously. The rate of PSHA allows you to consider multiple faults and earthquake source, and end up you will increase the chance of the hazard rate. And also this gives you a lot of information. If you look at this hazard curve, it tells you at lower PGA, fault A is the dominant one. But if you go to a higher level of shaking, fault B, give you a higher chance to be happens, which makes sense because a fault B, you have a larger magnitude earthquake, to take care of. So that's why you give you a higher chance to create those a mega size earthquake than fault A. But in a lower level of shaking, we're more likely the coastal one, will give you more chance to jeopardize your site for seismic